Welcome to solverfy.
In this problem, we have three materials with three different indices of refraction, N1, N2, and N3. We're told that N1 is at 1.68 and N2 is 1.59, that's a 9, and N3 is 1.5. This middle layer with index of refraction N2 has a thickness L. We're going to shine light with a wavelength of 342 nanometers. Now they don't actually specify, but I'm interpreting this wavelength as the vacuum wavelength. So the vacuum wavelength is 342 nanometers. So what's going to happen is the incident ray is going to partially reflect off of the first surface, going from N1 to N2, and partially transmit. That transmitted ray is then going to reflect off of the back surface between N2 and N3. And then those two reflected rays are going to interfere with one another. And they want us to find the distance L such that these two rays completely interfere, meaning they're completely out of phase. So that means that ray 1 and ray 2 have to be off by half a wavelength. All right, so the path length difference between these two rays is going to be twice the thickness L, right? Once you travel once to the left a distance L and once to the right, once to the right a distance L and once to the left a distance L. So 2L must be some half multiple of the wavelength. So we can write that as lambda times m, where m is an integer, plus 1/2. Right, but we have to be careful because it's lambda inside this material with index of refraction n2. So I'm going to write it lambda sub n. There's one more thing we have to account for, which is when you go from a lower index of refraction to higher index of refraction, the reflected ray gets shifted by half a wavelength. So we have to account for that. As you go from N1 to N2, you're going from higher to lower. So there's no phase shift on this first surface. And the same thing when you go from N2 to N3, you're going from higher to lower. So there is, again, no phase shift. So that works out. We don't have to add anything here. We just have to solve for L. We also have to know what lambda sub n is. So lambda sub n is just going to be lambda vacuum over the index of refraction, which in this case, right, it's this material in this green area here. So that's N2. So in total, we have that the distance, the thickness, has to be lambda times m plus 1/2 all over. We have a 2 from dividing from this left side of the equation here, and then times N2 on the bottom. And they want us to find the second minimum thickness. Well, the minimum thickness would be if you set m to 0. That will make this whole right-hand side of the equation the smallest. So this next one would be setting m to 1, right? So we set m for the second minimum thickness. And then we plug in all the numbers, and we find that L equals 161 nanometers.